Let's look at more examples of exponential functions, including population models. Recall that an exponential function has the form p naught a to the t, where p naught is our original amount, or p of 0, and a we can write as 1 plus r, where r is the relative change. Recall, when we looked at the populations of Williamsburg, Mass. In New York City, it was useful to talk about relative or percent change. If a population has a constant relative change, which means it grows the same percent each year, then we can use exponentials to model population growth. This often happens. Let's look at a biology example where we are growing a bacteria colony on a petri dish. Say we start with 160 bacteria in the colony. After 1 day, the colony has grown to 240 bacteria. After 2 days, the colony has grown to 360. And after 3 days, the colony has grown to 540. Let's find a model to describe the population. To do this, let's keep track of the population we have in a table. We start with 160 bacteria, so P of 0, or the population after 0 days, is 160. P of 1 is 240. The population after 2 days is 360. And finally, P of 3 is 540. To find our model, we need to figure out what P naught and A are. Well, to find P naught, we are looking for P of 0. But we know that P of 0, or P naught, is 160. So we're halfway done. To find what A is, we need to calculate relative change over 1 day. The relative change from t equals 0 to t equals 1 is 240 minus 160, our change in population, divided by 160, our original population for this time interval, which is 80 divided by 160, or 0.5. If we choose the time interval t equals 1 to t equals 2, then relative change is 360 minus 240 divided by 240, or again 0.5. On our last interval, from t equals 2 to t equals 3, relative change can be calculated as our change in population, which is 540 minus 360, divided by the original population for that time interval, which is 360. This simplifies down to 180 over 360, or 0.5. As we expected, our relative change over any 1 day time interval is the same and is 0.5. Since our exponential growth rate r is 0.5, a must be 1.5. So we found that P naught is 160 and a is 1.5. If we come back to our example, where we are trying to model the population of a bacteria colony, we get that P of t equals P naught, 160, times a to the t, or 1.5 to the t. So P of t equals 160 times 1.5t, where t equals the number of days and P of t equals the population after t days. Let's further look at this example. Using the model we just found, estimate the population of bacteria after 10 days. The phrase population of bacteria after 10 days is referring to P of 10. Evaluating our function at 10, we find 160 times 1.5 to the 10, or 9,226. So according to the model, the population of the bacteria colony after 10 days is 9,226.